Okay, now let's talk about the forces acting on a car that's going over a hilly roadway. All right, now let's look at the car at this location on the top of the hill, and let's assume the car is moving at a constant speed to the right the entire time. Now, when this car is going up the hill, it has a natural tendency to keep going up. So when it gets to the top of the hill, the normal force is going to decrease because the car has that natural tendency to keep moving up. The road doesn't keep going up, so they lose a little bit of contact. So if you look at the forces acting on this car at the top of the hill, there's a gravitational force down and a normal force up. And the size of N is smaller than the gravitational force. This means there's a net force down. That net force is called the centripetal force. All right, so in order for this car to navigate this curve, there has to be a net force toward the center of the curve, or else the car will keep going off on a tangent path. Now, this net force toward the center of the curve is called the centripetal force, which equals mv squared over r. Now, if we look at the force diagram, the size of the net force toward the center would be the size of W minus the size of N, right? This force going up is going to cancel out some of this force going down. Now, if I solve this for N, so add N to both sides, subtract mv squared from both sides. Maybe not the most efficient way to do it, but my normal force, the size of my normal force is smaller than the size of the weight by this mv squared over r. Now let's come over here at the bottom of the hill. Cars going down the hill has a natural tendency to want to keep going down. The road doesn't go down. The road gets in the way. That's going to increase the size of the normal force. I'll draw my force diagram up here. Now if you look at the forces, I exaggerated that maybe a little bit, acting on the car, the size of the weight doesn't change, but the size of the normal force does change. Now, there has to be a force toward the center of this curve, or net force toward the center of this curve, or else the car will fly off in a tangent path. Okay, that net force happens because the normal force is larger than the weight. I should say the size of the normal force is larger than the size of the weight. All right, now, so there's a net force toward the center. All right, now in this case, toward the center is up. That equals mv squared over r. Now if we look at this, the size of the force up is N. Some of that's going to be canceled out by W. So the net force, the size of the net force toward the center is the size of N minus the size of W. Now, if I add W to both sides, that's the size of the normal force at the bottom of the hill.